Hi, Lisa. Thank you very much for that nice introduction. And a good afternoon or good morning to everyone here. Thank you very much for attending today's webinar on autonomous vehicles and the evaluation of roadway marking systems. So the goals of today's webinar are to give you a brief introduction into what goes into making a good road stripe and to show you some technology that makes evaluating the performance of that stripe both for human drivers and computer drivers simple and efficient. So whether you're evaluating a single project's performance, performing R&D, or assessing an entire roadway system, mobile pavement marking assessments can really work for you. And so real quickly, this webinar has been divided into four main sections. We'll first discuss the what, why, and how of automated vehicle implementation, which is a subject I'm sure most of you are already well versed on. Next, we'll discuss RoadVista's Laserlux AV technology and how it works and operates, then show you the data it produces. And finally, I'll show you how we've adapted this technology to evaluate road stripes for machine vision. And following that up, we'll have a Q&A session at the end of 10 or 15 minutes. But before we get too far into the presentation, I wanted to give you guys a little bit of background about our company, about who RoadVista is and who Gamma Scientific is, since some of you may or may not be familiar with it and that may be confusing to you. RoadVista is a division of Gamma Scientific. Gamma Scientific started in 1961 with its first equipment manufactured to measure gamma correction curves of CRT monitors. So since the beginning, Gamma has always been one of the world leaders in precision light measurement instrumentation. We currently provide standard and custom instrumentation for markets such as LEDs, display market including virtual reality and augmented reality displays, heads-up displays, near-eye displays, etc., things like that. We also provide image sensor and camera testing and calibration through some of our digital and tunable light sources. We also offer test and calibration services through our ISO 17025 accredited metrology laboratory, and also the roadway safety industry, which is mostly the RoadVista branded product line. Our instrumentation has been used and trusted by dozens of Fortune 500 companies that require precision measurements for their requirements. And our headquarters and R&D manufacturing are all based in San Diego, California. And RoadVista, like I said, is a wholly owned subsidiary of Gamma Scientific, and it operates out of the same headquarters in San Diego. Now, as I touched on in the previous slide, our business is broken up into 5 main segments. Central to all the segments is our accredited laboratory. It's this lab that allows us to develop world-class measurement equipment to our diverse customer base. The business segments include spectroradiometers to measure color and brightness for various display applications, including automotive displays, precision lamps, including tunable LED sources for camera and sensor calibrations, photometers, radiometers, and colorimeters, including the photometer system used by IIHS and many auto manufacturers for headlight distribution testing, and roadway safety, which is a RoadVista product line and topic for this discussion. So with that, let's jump into the agenda. So the first topic for the agenda is autonomous vehicles, which is the what, why, and how of automated vehicle implementation. What do we think of when we hear talk about autonomous vehicles? Many of us tend to think about these cool sketch drawings of all these futuristic cars, though the audience of this webinar may be the exception to that. You guys know a lot more than a lot of the general public does. But actually right now, as you already know, we're already testing different levels of automation, including level 5 vehicles. Level 5 being the top level, which I'll talk about more coming up. But it's more than just level 5. Right now, most cars already have a tremendous amount of automation in them, which includes, for example, lane keeping systems, blind spot warning systems, adaptive cruise control systems, things like that. So the roads are already being driven on by vehicles with some automation in them, which is quite exciting. So vehicle automation, what is it? There are 5 levels of vehicle automation, which I'll go over very quickly. Most of you probably already know more about this than I do. Um, Level 1, which is driver only, there's really no systems beyond maybe ABS, for example. This would be your older model basic car with all manual control systems. Level 1, which is assisted, driver carries out all lane holding or lane changes, but the vehicle takes care of other functions. An example like that would be cruise control or something like this, where the vehicle is able to take over some part of the driving. Level 2, this is a level we see a lot on the roads right now. The driver must continuously monitor the system, but the system handles the lane holding and lane changes and other special cases. For instance, your new cruise control, which is adaptive and keeps you a certain distance away from the vehicle in front of you. Or if you start to drift out of your lane without using your turn signal, the system will have some kind of audio or tactile feedback to warn you. Then we get into level 3, which is highly automated. In this level, the driver no longer needs to continuously monitor the system, but needs to be there to take action or take over if necessary. And I've actually had the opportunity to drive a Tesla Model X with level 3 automation, and it will handle lane changes on its own just by using the turn signal. Pretty neat, the levels that we're getting to right now with this. Now with level 4, the driver is still there, but basically not driving the vehicle. And with level 5, the driver is no longer needed or there. As most of you know, level 4 and 5 vehicles are currently being tested, but right now on the road we're seeing a lot of level 2s and a few level 3s in the higher end vehicles. There are also two acronyms that I want to make sure you all are aware of, even though many of you already are. V2V, which is vehicle to vehicle communications, and V to I, which is vehicle to infrastructure. For us, primarily in the transportation industry, we're mostly talking about V to I, which is what the Laserlux AV is designed to enhance. So why do we want vehicle automation? According to this report from the Florida Department of Transportation via the US DOT, almost all crashes are human error. In fact, 99% of all crashes are human error. You can see the different types in this charts. They're kind of spread out for various different reasons. Driver inattention takes about 23%. Speeding's 19%. Alcohol impairment is 18%. Perceptual errors, like the driver looked but didn't see something, made a move anyway, that's 15%. So you can see there's a lot of different reasons why accidents happen, and if we were able to take the human error out of it, we're way down the path of greatly reducing accidents. That's where machine vision starts to come in. Machine vision is the key tool in vehicle automation and gives the computer the ability to see what's around it. The systems typically employ one or more cameras, and in most cases there are many multiple cameras. Sometimes 8 or more cameras can be used. The data in the cameras gets interpreted by the computer, which sends signals to robotic controllers to react accordingly, and action is initiated based on data. So that leads us to pavement markings versus machine vision. First off, when we say pavement markings, we're talking about the lines painted on the road, in case any of you weren't aware of what a pavement marking is. This chart here shows you that 51% of all crashes are a result of run off the road, with a breakdown showing in the chart. 24% you run off the right, 10% to the left, and 17% hit the center median. So you can see maintaining lane position is very important. This is what these AVs are designed to do, and like mentioned previously, many of us are already driving cars that will warn us in some way when we start to exit our lane of travel. FHWA has stated that many vehicle manufacturers have reported to Congress that pavement markings are one of the most significant infrastructure elements needed to guide automated vehicles. And I'll say that one more time. Pavement markings are one of the most significant elements needed to guide automated vehicles. So ongoing research. A few weeks ago, I attended the Transportation Research Board annual meeting in Washington, D.C. One of my colleagues that sits on the sign and pavement marking committee with me said, if you don't fully understand how humans interpret roadway markings, how do you know what to program into the computer driver? When he said that, I really thought that hit the heart of the matter. We've been building roads for human drivers for hundreds of years, and it's always been a continuous improvement of safety, and that's been the whole basis for all our research. The steps to making roads safer for autonomous vehicles is just really the next step in the evolution in roadway development. But since our existing infrastructure has been geared around human drivers, the quickest path to AV implementation is to take advantage of the existing infrastructure and program the computers to interpret the roads the same way people do. So what are we doing to help this along? Road Vista has partnered with TTI, which is the Texas A&M Transportation Institute, on an NCHRP research project. The designation is 20-102 Part 6, which started in July of 2016, and we're just now finishing up Phase 1. The goal of the project is to help determine what makes a good pavement marking for machine vision. That's basically the mission statement for the research project. So what have we found so far? The preliminary findings indicate that a 2-to-1 contrast ratio between stripe and pavement typically gave good confidence levels of 2 and above from the machine vision cameras. In the daytime, contrast is what's needed. At night, retroreflectivity becomes the driving factor, and good retroreflection becomes more and more important the farther out the cameras are looking. If you don't know what retroreflection or retroreflectivity is, don't worry about it right now. I'll get into that coming up shortly. So as we enter Phase 2 for the project, we're asking for help from the AV industry. Anyone who's willing to share or provide some of their technology at any level would help us out greatly moving forward in trying to understand how to make our roads quote-unquote autonomous vehicle ready. Even filling out a brief survey would be helpful. So if any of you are interested in helping out, please contact me directly, or you can reach out to Adam Pike at TTI. He's the head researcher on this project, and his contact information is on your screen. We really appreciate any help you're able to provide with this. So as I mentioned, I've had some first-hand experience with a level 3 autonomous vehicle. One anomaly in the system I discovered was a situation where I was driving down a 2-lane road, and the center line moved towards the left to make room for a left turn lane. When the vehicle got up to the lane, it made an abrupt jog to the left since it was tracking the center line. It also probably didn't help that at the same time the right edge line turned towards the right, so the machine vision system was receiving conflicting information. In this case, it determined the autopilot was primarily following the center line, which caused the abrupt jog to the left. Well, what I was thinking is, if the camera were looking further ahead, it could potentially pick up the lane line way out in front of the vehicle that I've circled in red up there. That way the vehicle could be kept driving in a straight line. And this is where potentially the retroreflectivity line can become an important factor in the implementation of autonomous vehicles. Any additional information that the vehicle is able to receive will help out greatly in fixing these little anomalies, like the vehicle trying to keep going along the center line the way it is instead of tracking a straight line in the lane. So now let's get into the features, operation, and data that comes out of the Laserlux AV, including what makes a good road stripe and how we go about measuring it. So what makes a good road stripe? There's actually a lot of engineering and technology that goes into it, but it can be broken down into two main features. The first one is the binder. This can be a variety of materials, which will give you a durable line that can last many years, or a less expensive short life line. A lot of the choice of the binder material depends on the roadway type and its location or climate, but the binder is primarily what gives the line visibility during the day, but also provides the base for the other key component, which is the glass beads. Again, there are many various types and sizes depending on the application and desired performance level, but no matter the type, the glass beads enhance the visibility at night or whenever there is a projected source of light near the viewer, whether that be a human eye or a machine vision camera. So how do the glass beads work? The beads partially embed themselves into the paint, so they're partially exposed. You can see a couple photos here. One's kind of a far away view that shows you the glass beads, and then the photo on the right shows you a close-up photograph of what glass beads look like in a pavement marking. To diagram that out a little bit, the beads partially embed themselves in the paint, so they're partially exposed, and then light coming from the headlight of the vehicle will illuminate the bead and enter into it. Due to physics, the light bends a little bit and hits the back wall of the sphere, where most of the light will then be reflected off the back wall and exit the sphere near where it entered and return back from where it came from. Because of the bonding between the glass bead and the binder, the reflected light will take on the color of the binder, and so that's how you get yellow and white pavement markings, primarily yellow and white, and that's how they maintain their color at night. So what exactly are we measuring? In a typical vehicle, the driver is inside it looking forward and down the road. The driver also typically sits higher than the headlights. The road stripe is typically illuminated in one of two ways. During the day, it's the sunlight that lights up the stripe, and that can either be direct sunlight or diffuse sunlight, either through clouds or being shaded by another object. At night, the primary source of illumination comes from the vehicle headlights. There can also be roadway lighting that would illuminate the stripe, similarly to how the sun illuminates it. But in either situation, the driver sees the light that reflects off the stripe in their direction. But why do we make mobile measurements? Well, they're really safe and efficient and give us a quick means of being able to evaluate roadway systems to determine the quality of lines on the road without disrupting the flow of traffic. They're also very efficient, so that we can measure hundreds of miles of road every day and really quickly be able to map out good areas and bad areas on your roads. So let's take a look at this slide here. Both of these videos are showing a roadway that is undergoing a restripe. This is the same section of roadway, but obviously on the left video it's daytime and on the right video it's nighttime. We're driving in the center lane there, so we're looking at the dash lines indicating the lane for this lane of traffic, and you see during the day both the left lane line and the right lane line look fairly similar. They're both fairly visible and they look pretty good. But if you go over and look at the night video, then the line on the left appears much, much brighter than the line on the right. If you look at the contrast of them, during the daytime, we get fairly good contrast with both of them. The left lane line is 2.9 to 1 and the right lane line is 2.2 to 1, which are both in the levels excuse me, that the machine vision cameras will consider fairly good and give high confidence levels. But if you look at night, the line that has a retroreflectivity, that contrast really jumps up very high, and so you get very good contrast, very good visibility with it. And to give you some reference, you're looking at 600 to 700 millicandela per meter squared per lux, which is the units of retroreflectivity. And that kind of tells you how bright the lines are for how much illumination is falling on them. But you notice the right lane line in this situation, you're looking at 60 to 90 millicandela per meter squared per lux, and that's giving you a 2 to 1 contrast ratio, which is really right on the threshold for the machine vision systems to be able to give high confidence level in their ability to see the stripe. So what all this means is that lines that are visible in the daytime are not necessarily visible at night. But the opposite is not true. Lines that are visible at night are almost always visible during the day. And this is because for lines to be visible at night, they really need to have good retroreflectivity with a lot of glass beads on them. And the only way for the glass beads to remain in the position are for they to be embedded in some kind of binder. And in this case, the binder is the paint on the road. And if there's paint on the road to hold the beads, then that paint's going to be visible during the daytime. But what the advantage of retroreflectivity does is it allows the line to be seen at a much farther distance, and so it becomes more and more important as the cameras are looking farther forward for the retroreflectivity to be really good. So now we get into the design of the instrument here. As you can see, it's approximate size 10 by 10.5 by 20 inches, and it weighs approximately 25 pounds. And how does it work? Well, what we do is take a diode laser and we fan it out by bouncing it off a resonance scanner, which projects a horizontal line out in front of the instrument. The laser is pulsed in sync with the resonant frequency with a 50% duty cycle, so that we're able to eliminate all ambient conditions and just measure the stripe and the road itself with nothing else involved. The return signal is measured in sync with the laser pulse with a detector inside the unit, and what this allows for is for measurements to be made day or night with no variations in the measurement. What we're doing is we're scanning the pavement 400 times a second, so that gives you pretty much continuous coverage every 2 inches of road at 65 miles an hour. And the area of measurement is 1 meter wide by 20 centimeters long. So if you figure that one out, it's 1 meter left to right and 20 centimeters along the direction of travel fore and aft. So that even at 65 miles an hour, when you're going at making a measurement every 2 inches, the swath of that laser is a lot more than 2 inches long, so you are getting continuous coverage of the line. That way we make sure we don't miss any sections of that line. So when you record the data, the user can define the number of readings it averages, which controls the volume of data, and typically that's 1/10 of a mile for most jobs that are out there that are being measured. But for research purposes or other reasons, we can cut that down to as little as 5 feet to make readings every 5 feet if you really wanted to look at the uniformity of the line and how well it worked. The instrument will also detect and count raised pavement markers, otherwise known as road studs or cat's eyes, but these are the little plastic reflectors that stick up on the road if you're not familiar with them, that give enhanced retroreflectivity and give some tactile feedback to the driver. If you run over them, you can actually feel and hear your vehicle run over. It'll also measure the perceived width of the line. Since we're getting a profile of the line sweeping across it, we're able to measure how wide that profile is, so that'll give you an idea whether the line is 4 inches or 6 inches or actually appearing that way at night, and that'll give you a good indication. You know, if you've got a 4-inch wide painted line or a 6-inch wide painted line, but you're reporting a width of only 3 inches, well, then that means that the bead gun that was on the paint truck or the striping truck when it was painting the line did not do a very good job of dispersing the beads, so you don't really have a good quality line out there. And it's also got a built-in humidity sensor to just to monitor the ambient humidity and also temperature. It's got a thermometer in there as well, because those can have some effect on the retroreflectivity of the line. We also record high definition video, which is synchronized with the data and the data will be displayed in the video for playback, which will provide you a nice means of being able to review the data afterwards. You can go back and actually get a visual on that section of road. If you looked at the data table and something didn't look right, you can actually go back and look at that video and see what may have been causing that problem. And it's a good, very useful tool for getting that done. Calibration of the equipment is very simple. It takes less than 30 seconds, and it will provide you a traceable data that correlates with historical pavement marking measurements. So that way you can always know in the future what when you collect your data, it's going to correlate with data that was taken in the past. So you can have a historical record of how a roadway or a line has worked over time. So the instrument is completely wireless control except for one power plug that plugs into the cigarette lighter. But there's no need for any special computers or extra devices for it. It runs off of any computer, tablet, or smartphone that has a Wi-Fi connection. And it creates its own local area network. You can have multiple devices connected to it, and doesn't require any other cellular or internet connections. And as I was saying, it's compatible with any device out there, since we just use a web browser and Wi-Fi. Any smartphone, tablet, or computer with Windows, OS X, iOS, Linux, Android will work with it. It really doesn't make any difference. It's very user-friendly in that way. It also comes with a removable USB drive. This is where all the data gets stored. Comes standard with a 64 gigabyte flash drive, which gives you about 20 hours of high definition video, but can easily be swapped out. And during the day, if you run out of space or need to do something else, you can pull it out, put a new one in, or at the end of the day, you just pull the USB drive out, and all your data is right there. You can plug it in your computer and take a look at it, do analysis, post-processing, whatever you want to do with it, without having to wait to download it from the instrument or any other device. So the features of the equipment, one of the most innovative one is the Squid mount system. This securely adapts it to most any vehicle without any modifications to that vehicle needed to be done. If you were in California and you needed to go measure some roads in New York, it's simple as packing the thing up in its case that it comes with and shipping it out to your colleagues in New York, or you could actually check it as baggage on the plane, fly it out there, rent a car, attach it to the car in about 10 minutes, and you're ready to go. There really are no modifications needed to the vehicle. The other key feature is the automated positioning system. This has got two height sensors on the bottom that continuously measure the distance between the instrument and the pavement. What this does is it ensures consistent geometry with the measurement, so that we can make sure that all measurements correlate with each other and they are consistent. So from vehicle to vehicle, from day to day, from setup to setup, the instrument's always in the same position, therefore it'll always give you the same results. So a little more about the Squid mount system. And what it is actually a system of vacuum cups that attach to the side of the vehicle. And we built a little overkill into it. The whole system with 5 cups will support about 500 pounds, and as I said, the instrument was only about 25 pounds, so we really go overkill on it. And what's key about this is that these are not suction cups, which is something, most of you are familiar with it. You may have to lick it or anything, but you just kind of push it up against some surface and it'll hold. These are actually vacuum cups, and they're used to support very heavy objects. There's actually a pump on them that allows you to suck out all the air and make the rubber cup completely flat against the surface, so you're actually using the full force of atmospheric pressure to hold the equipment to the side of the vehicle. And this system works very, very well. In fact, we've never lost one off the side of a vehicle. We have had customers hit these things on curbs. We had one customer hit their instrument on a center divider going 45 miles an hour, and it stayed on the vehicle. It did not move. So it's a very, very solid system. It works very, very well. And what's great about it is it doesn't require any permanent vehicle adaptations. You can just attach it to your vehicle, any vehicle you have right there, and at the end of the day, take it off, and your vehicle's back to being a normal vehicle again. No extra mounting hardware or anything else involved with it. So now a little bit more on the automated positioning system. Like I said, it keeps the Laserlux at a fixed height above the pavement. It's got two stepper motors that will drive the instrument up and down. In this video here showing a little bit of an animation to show you what would happen if the roadway was moving up and down. So you can see it can both lift, keep it in the same plane, or it can tilt the instrument forward or backwards to maintain the proper geometry for the measurements. Now, so as you're driving down the road, this slide gives you kind of a view of what you'd be seeing here. On the left is your user interface, which is showing you that stripe profile. And you can see the squiggly line is kind of the real-time measurement of the line, and the green box is what the software is interpreting as being the line itself, the average of the line over whatever the interval is. I can give you an idea. The video on the right hand side showing you what you'd see afterwards. You can see up at the top of that you've got the data from the user interface showing you GPS coordinates, the value for the line, your odometer reading, date and time, and that kind of stuff. So since the video is broken up into 5-minute increments, and when you're going to look through the data at the end, it makes it really easy to go back and when you see something that looks funny in the data, you can go back and look at this video and see what was going on at the time. So now you have all this data. Well, what do you do with it at the end? We'll show you in the next few slides here the data that you get and the things that you can do with that data. What the instrument provides is 3 main files. You get a CSV file, which is just an Excel spreadsheet file. Tabular data that allows you to look at the actual numbers of all the data. You also get a KML file, which is a Google map or Google Earth file, which will be a color-coded map showing you color-coded lines depending on what the value is, so you can easily find good lines, bad lines, marginal lines, things like that. There's different levels of color coding. I think you can do up to 5 different levels of different colors just to mark the data for different ranges of values that are in there. And you also get high definition video, an MPEG file for playback. This will include the data overlay on it, so you'll get the actual data for the date, time, location, the value of the line. That all gets overlaid on the video, and you'll get a dashboard camera video of the roadway as you're driving down the road. So give you ways to analyze and look at the data different ways for your analysis of it. So here's an example of the table of data that you'll get out of the instrument. You see up at the top there's some header information, give you the file information, some of the settings of the equipment, and below all that it gives you your table of data. You get your odometer reading, date, time, GPS coordinates, vehicle speed, temperature, humidity, and all the values and readings on the lines that you are measuring. And it's fairly straightforward, fairly easy to look at. When you get to the next step, there's a report generator That's an Excel macro that will allow you to create a little more visual report, so you can get a plot of the data. So you can see for this particular example, that line plot up at the top showing you the values were decently well. That red line at 200 is showing you what the minimum value was for that section of the road, and you see most of it's between 300 and 350, which is a pretty good line, except one little section there dipped way down. And part of this report generator, see that there, it will flag that data in the table. So as you scroll down to it, you'll see these red cells, and that will correlate well with that that plot up at the top, so you can quickly see where the bad sections were. And if you had marginal sections, they would show up yellow. So different ways to look at the data, and this makes it, we try to make it as clear and simple to do. And as we talked about before, you'll get the video with the data overlaid on top of it, so you'll get to see as you're driving along, take a look at the video, get an overall view of what the roadway looked like, and see the actual data up at the top. When we put these things together, we break up the videos, and they're saved into 5-minute increment. Each 5 minutes of video is a separate data file. So when you're looking through the data, you can see the timestamp on the data. You can look at the GPS coordinates, and you can go to that corresponding video file. So you don't have to sit there and scroll through hours and hours of video. If you know exactly what time in the table of data showing you the batteries, you can actually just go right to that section of video and pull that up and take a look at it. You also get the Google Earth map, and you'll zoom in on an example. You can see the line there. It looks like we were doing that edge line, kind of going to the northwest there. And you can see it turned from green to red. So you can see this section of the line was poor quality for whatever reason. What you can also do with these maps is you can click on any point along that line, and it will pull up a table of the actual data that's there. So you'll get the same kind of tabular data that you see in the spreadsheet file will show up in this map file for you to take a look at. So after you've driven a lot of roads with the instrument, you'll end up with these nice map files that will show you a lot of detailed information. You can see this one measured quite a number of roads in this area, and user of the equipment also added some notes to notate things like going over a bridge or pavement change from asphalt to concrete or vice versa. What else you got on there? There's a construction zone in there. But the user is able to annotate the data as they drive, so you can put these flags in the data when you look at it. You can also zoom on sections of this data to get a really detailed picture of what each roadway looks like. And you can see in this particular case, some sections of the roads, if it's two-way direction, you've got 2 or even more, depending on how many lines you're doing. You got different color lines, depending on which line it was they were measuring in the road. So this really gives you a detailed overview of everything going on, and you can quickly look at it and say, hey, we need to concentrate on this section right here, like at this interchange. Kind of above there's a lot of yellow and orange and red, which means those are kind of marginal, and the red ones are actually probably some pretty poor markings that should be looked at. So Laserlux vision system, what is it and what are we doing with it? Well, we're preparing for the future and providing for the present at the same time. Add-on feature we've added to the equipment. What we're dealing with is human vision versus machine vision, and obviously human vision, we're limited to the visible light of the spectrum, which is all we can see, which is wavelengths 360 nanometers to 830 nanometers. So this is your typical red, yellow, orange, green, blue light that we all see. As we're driving down the road, we see both color and contrast, which gives us cues on how to interpret what we see. But the advantage of machine vision is it isn't limited to just the visible region. The visible region is certainly part of it, but machines also have the ability to see things that we cannot outside the visible spectrum of light. In the world of AVs, this has mostly been implemented in the infrared region, but there have also been some systems that will look at UV light as well, ultraviolet light. So with machine vision, you can take advantage of things that humans can't see. So how does that relate to the Laserlux AV system? One option with the system is we can simultaneously evaluate pavement markings for both human and machine vision at the same time. And we do this by deploying two different lasers. One's a visible laser to measure the visible light for humans, and one of them is an infrared in the one we've done, but we could easily do a UV laser as well if someone was interested in that. But for the most part, it's been infrared visibility. And that way we get two different data files coming out of the instrument. Remember we were talking about the CSV spreadsheet files. If you have the vision system option on the instrument, then you end up with your regular file showing the values for the visible retroreflectivity, but you also have a separate file that's showing you the infrared retroreflectivity values and infrared visibility, which allow you to get values so you can correlate machine vision cameras with their scaling system to retroreflective values in the infrared, and also correlate that human vision, so that when you go back and look at historical data, you can say, hey, since I know this particular line happened to be 250 millicandela per meter squared per lux, which is a pretty good value for humans, that correlated to such and such value in the infrared, and that correlated to such and such value on our machine vision camera. So it gives you a good tool to be able to get correlation between all the different ways that these lines are being measured. So these values can be placed, like I said, in rating bins from 1 to 5 to determine the quality. And right now, actually part of that NCHRP study and some other studies that are out there, the process of correlating these infrared retroreflectivity values to the, in this particular case, it's the Mobileye rating system that's used in many of these autonomous vehicle systems. So you can see these lines courtesy of TTI, or these images courtesy of TTI here, showing level 3s, which is good confidence level, and one level 1 there on the right hand side of that daytime video, showing you kind of poor confidence level line. We can actually use those values and correlate those to real measured retroreflectivity values, which can be a useful tool for you. And as you know, it's pretty linear relationship here. As the retroreflectivity value of the line increases, the confidence level in your ability to pick out that line is also going to increase. Retroreflectivity is a key tool in making sure that lines show good visibility out on the road, and in turn that'll make it easier for machine vision camera systems to be able to pick that up. So to close out, mobile pavement marking assessments can achieve accurate, comprehensive data quickly and safely. They're very fast. It's very adaptable, so you can attach it to almost any vehicle out there, making it really easy to implement. Operation is very simple. It just requires one wireless device, whether it be a smartphone, tablet, or computer. User interface is very intuitive, very easy to learn very quickly, and you get a lot of data out of it. Between not only the retroreflectivity, but you get the contrast, you get the line width, counts RPMs if that's of interest to you. It'll show you the roadway attributes, and it's all in tabular format in a spreadsheet data, you also get the maps, and you also get the video. So it's a really comprehensive system. And adding the vision system for infrared measurements makes it even more useful and even more powerful tool for you to use out in the field. Now, so before we close out the presentation portion of this webinar, talk to you about a couple other products that Road Vista manufactures that might be of interest to you. We have the Stripe Master. There's a few different versions of it. It's a handheld instrument that will evaluate pavement markings as a spot checker. In case you didn't have a vehicle or want to go out and measure a whole section of road, if you just had a little small section to measure, Stripe Master instrument's a good tool to get out there and make a few spot measurements, check to see the quality of your line. This would be a useful tool for a small test deck. If you're out there, you can go out and evaluate your road markings while you're there. Another instruments are the Model 922 and 932. These are handheld instruments to evaluate road sign performance, specifically the retroreflectivity, both in the visible region, and we also have a version of the instrument that will measure the infrared retroreflectivity. Know out there that there's a manufacturer that's making some overlays for the signs that would change the way the retroreflectivity is in the infrared. And this tool with the infrared retroreflectivity measurement option would be a good way to evaluate the performance of that and see what kind of contrast levels you're getting in the infrared, so you can see how well your machine vision cameras would work. And with that, I'd like to thank everyone for attending, and I will now hand it back over to Lisa. Thank you very much again, everyone.